All right, welcome back, everyone. Today, we are going to dive into something absolutely fundamental in circuit analysis. What happens with voltage in a parallel circuit? You know, this is one of those rules that once it really clicks, so many other things just fall right into place. So let's get into it. So you already know that in a series circuit, right, the voltage gets split up across all the different components. But what happens if we change the game? What if we give the current multiple paths to go down, kind of like the rungs on a ladder? Does that voltage still get divided? Let's find out. First up, we're going to lay out the single most important rule you need to know for this, but more importantly, we're going to break down why it actually works. Understanding the why is everything. And there it is. That's the rule. In a parallel circuit, the voltage is exactly the same across every single branch. So if you've got a 12-volt source, every single component hooked up in parallel with it sees the full 12 volts. No sharing, no dividing. It's honestly that simple. But why? This right here, this is the secret. Look at that bottom wire. You see points A, B, C, and D? There's nothing between them but wire. That means electrically, they're all the exact same point. We call that a single node. And guess what? It's the same story for the top wire with points E, F, G, and H. So every single resistor is connected between the exact same two nodes. And since voltage is just the difference in potential between 2 points, well, they all have to have the exact same voltage. And this brings us to a really, really important skill: learning to see past how a circuit is drawn. It's so easy to get fooled by the layout, but what really matters are the electrical connections underneath. Just take a look at these two diagrams. On the left, you've got that classic ladder look. On the right, it looks a little different, maybe a bit more compact. But are they actually different? Nope, not at all. In both drawings, the left side of every resistor connects to one big node, and the right side of every resistor connects to the other big node. They share the same two connection points, so electrically, they are 100% identical. Don't let the way it's drawn trick you. Okay, so theory is one thing, but you know me, I like to see it in action. The best way to know something's true is to measure it. So let's pretend to build this circuit and slap some voltmeters on it. So here's our setup. We've got a 12-volt battery connected to 3 resistors all in parallel. And we've wired up 4 voltmeters, one to measure the battery itself, and then one across each of those 3 resistors. Now, what do you expect them all to read? Okay, let's check the meter across that first resistor. It's connected right across the source and, yep, just as we'd expect, it reads 12 volts. Simple enough. Now, what about the next one? We move over to the second meter, across the second resistor, and look at that, 12 volts. Exactly the same. No voltage drop, no change whatsoever. And just to be sure, the third meter confirms it, 12 volts. This is the real-world proof of our rule. Every single branch sees the full voltage from the source. It's not just a theory. And this is how we would draw that exact same circuit on paper. This is the schematic, the blueprint. The picture before shows us what it is, but the schematic tells us how it's connected for our analysis. You see the source, Vs, and each resistor sitting right across it. So, we know the rule, we've seen the proof. Now it's time to actually put this knowledge to work and solve the kind of problem you'd see on a homework assignment or an exam. And you're going to love this, because the process is so straightforward. Step 1, just identify all the parts that are in parallel. Step 2, remember the rule. They all get the same source voltage. And step 3, just state that voltage. That's it. It's really that easy. Let's try this one. We have a 25-volt source and 5 resistors, R1 through R5. The question, what's the voltage across each resistor? Well, let's use our steps. First, are they all in parallel? Yes, they're all connected between the same 2 points. Those 2 points are connected to the source. Therefore, the voltage across R1, R2, R3, R4, and R5 is, you guessed it, 25 volts. Done. Okay, now for a quick curveball. What if we just pluck R4 right out of the circuit? What happens to the voltage across its neighbor, R3? Does it change? The answer is not at all. R3 is still hooked up directly across that 25-volt source. Taking away another parallel branch doesn't change a thing for the others. The voltage on R3 stays at a solid 25 volts. All right, I think you're getting this, so let's put that new knowledge to the test. I've got a few quick questions for you. Try to answer them in your head before I give you the answer. Okay, question 1. You have a 100 ohm and a 220 ohm resistor in parallel with a 5-volt source. What's the voltage on each? It's 5 volts. Remember, the resistance value doesn't matter for the voltage. Next, number 2. A voltmeter across R1 reads 118 volts. What's it going to read on R2? Well, since they're in parallel, it's got to be 118 volts, which also tells us the source voltage is 118 volts. Good. Question 3, looking at that figure. What does V1 read and V2? V1 is across the source, so that's easy, 50 volts. V2 is across a parallel resistor, so it also must be 50 volts. And finally, the big one, how are voltages across each branch related? They're all equal. You know, if you ever get stuck or confused, just come back to this ladder analogy. It's so powerful. Think of the 2 long rails of the ladder as your 2 main nodes connected to your battery. Every single rung you add, that's a resistor, is just connecting those same 2 rails. So every rung has to be the same height, the same voltage. So if there is only one thing you remember from our time today, let it be this. In a parallel circuit, voltage is constant. It is the same everywhere. It does not divide. Get that tattooed on your brain. It's a critical piece of the puzzle. So we've totally nailed down what happens to voltage. It stays the same. But that opens up a really interesting new question, doesn't it? What about the current? The total current leaves the source. It gets to a fork in the road. In fact, it gets to multiple forks in the road. Does it also stay the same, or does it divide? Well, that's a story for next time.
Hello, everyone. Today, we're going to dive into one of the most fundamental rules in all of electronics, how voltage behaves in a parallel circuit. Now, it might seem tricky at first, but it's all governed by one simple, incredibly powerful rule. Once you really get it, a whole new world of circuit analysis is going to open up for you. So, let's get right to it. Here's our game plan. First, we're going to learn the golden rule itself. Then we'll dig into why it works by exploring something called electrical nodes. After that, we'll look at some visual proof, see it in action. We'll apply it to a real circuit problem, and then we'll wrap things up with a quick quiz to make sure this concept is totally locked in.
So, let's start with the single most important thing you need to know. If you walk away with nothing else today, remember this. In a parallel circuit, every single branch gets the exact same voltage. That's it. That's the secret. This one idea is the key to everything else we're going to do.
But just memorizing a rule isn't really good enough. We're engineers, we need to understand why it's true. And the whole reason comes down to a really simple concept, the electrical node.
Okay, so take a look at this diagram. See those points labeled A, B, C, and D? They're all connected by one continuous wire. Now, in circuit theory, we assume our wires are perfect conductors, which means there's practically no voltage difference between any of those points. Electrically speaking, they are all the exact same point. We call this a node. And you can see the same thing happening on the other side with points E, F, G, and H. That's our second node.
Now here's where it gets really cool. Watch what happens when we just redraw the circuit. Look at this ladder diagram on the right. It's the exact same circuit, we've just kind of stretched it out. And this makes the whole concept crystal clear. The 2 vertical rails of the ladder, those are our 2 nodes. And notice how every single component, every rung of the ladder, is connected directly across those same 2 rails. Theory is one thing, but seeing is believing, right? So let's move away from the abstract idea of nodes and look at a concrete visual proof of this principle in action.
On the left, we've got something that looks like it's right out of a lab. On the right, we've got the clean schematic diagram. But here's the key takeaway. Look at where the voltmeter is connected. It doesn't matter if we measure across the battery, across resistor 1, resistor 2, or resistor 3, the reading is absolutely identical every single time.
And for this circuit, that constant value is 12 volts. This is the whole point. The voltage isn't getting split up or shared. Every single parallel branch sees the full, undivided voltage from the source. It is constant. It is unchanging. Okay, so now that we've got the rule down and we've seen the proof, let's actually put it to work. We're going to use this theory to solve a pretty typical circuit problem. All right, here's a practical problem for you. We have a 25-volt source and it's hooked up to 5 resistors in parallel. The question is simple. What's the voltage across each and every one of those resistors? Now, before I just tell you, take a second and think about it based on what we've just discussed. I know this layout might look a little busier than that simple ladder diagram, but don't let it fool you. If you actually trace the wires, you'll see that the top of every single resistor connects back to one common point, and the bottom of every resistor connects back to another common point. They are all, without a doubt, in parallel with that 25-volt source.
So, solving this thing is actually a really simple two-step process. Step 1, just confirm that, yep, all the resistors are truly in parallel with the source. Step 2, apply our golden rule. The voltage across every single branch has to be equal to the source voltage.
And just like that, you have the answer. The voltage across the first resistor, it's 25 volts. The second, 25 volts, and so on, for every single branch. Each one experiences the full potential difference from the source. It really is that straightforward once you know the rule. Okay, you've seen the theory, you've seen an application. I think it's time for a quick knowledge check. Let's do a few rapid-fire questions to really make sure this is solid.
First question for you. You've got a 100 ohm resistor and a 220 ohm resistor. They're connected in parallel with a 5-volt source. What's the voltage across each resistor? Go ahead and think about it.
The answer is 5 volts. This is a classic question because it throws in those resistance values to try and trick you. But as we now know, for voltage in a parallel circuit, the resistance values are completely irrelevant. All that matters is the source voltage.
All right, let's move on to the next one. Take a look at this circuit here. We've got a source, two parallel resistors, R1 and R2, and you can see there's a voltmeter connected across R1.
So that voltmeter is reading 118 volts. Now here's the question. What happens if you physically move that meter, disconnect the probes from R1 and reconnect them across R2? What's the new reading going to be?
118 volts. And this just perfectly demonstrates our main point. Since R1 and R2 are in parallel, they are connected to the same two nodes, so the voltage across them must be identical. Okay, last checkup question. Let's take a look at the circuit in Figure 6-11. This time, we've got a 50-volt source and two different voltmeters, V1 and V2, connected into the circuit.
So the question is simple. What does voltmeter 1 read, and what does voltmeter 2 read?
And of course, the answer is that both voltmeters are going to read 50 volts. If you trace their connection points, you'll see they are both just measuring the potential difference between the circuit's two main nodes, the same two nodes connected to that 50-volt source.
So, after all these examples and all these diagrams, it really just boils down to this one simple, unwavering truth. The voltage across every single branch of a parallel circuit is always equal.
So, you've got a rock-solid grasp on voltage in parallel circuits now. But voltage is only half the story, isn't it? Which brings us to the next big question. What about the current? How does it behave? How would something like Kirchhoff's current law apply to the very same circuits we just looked at? That's a thought to chew on until next time.